We are a relatively younger group in the physics department of IIT Bombay. So this is my group, and broadly we are interested in understanding unconventional properties of materials. So this involves first the proper description of these complex material systems, followed by discovery of new physical properties, and based on the understanding of those properties, we try to design materials with unconventional properties. And the kind of properties we are interested in ranges from magnetism, hidden order, spin orbitronics, topology. In today's talk, actually I will focus on hidden order, which is something that we are currently working on actively. By hidden magnetic order, we refer to those magnetic order that are difficult to probe using conventional experimental techniques, but they do have important implications in understanding the properties of the system. And probably the first ever example of such hidden magnetic order was antiferromagnetism. So when this cusp in the magnetic susceptibility data of manganese oxide was first discovered, it was very puzzling at that point of time, because the only type of magnetism known was ferromagnetism, and manganese oxide doesn't have any net magnetization. Later, Neil pointed out that this is actually associated to a phase transition, where the neighboring immense spins are anti-parallel to each other rather than being parallel. This is of course very well known today as antiferromagnetism. And to describe antiferromagnetism, what we use is the concept of staggered magnetization, which is nothing but the difference in the sublattice magnetization. Now this staggered magnetization concept is very intuitive, but it lacks the convenience of not having any ferroic order in our system, like we have a ferroic ordering of electric dipole moment in a ferroelectric system, or a ferroic ordering of magnetic dipoles in a ferromagnets. Consequently, it does not provide any information regarding the field that I require to select one of these domains, antiferromagnetic domains. It also does not distinguish between antiferromagnets that do and do not break time reversal symmetry. However, magnetic dipole is just one term in this multipole expansion. So here what we see is the interaction energy between an arbitrary magnetization density and an applied magnetic field. And if we expand it in a Taylor series, we get the first order contribution, which is nothing but the dipolar contribution, the very well known Zeeman splitting. But if our magnetization density has asymmetries or anisotropy, then consequently we will have contributions from higher order terms like magnetoelectric multipole, magnetic octupole, and so on. Now something that I want to point out here is that all these magnetic multipoles, of course they break time reversal symmetry, but under inversion they behave differently. So for example, this magnetoelectric multipole breaks inversion symmetry because it has odd R dependence, whereas the magnetic octupole preserves inversion symmetry because it has R squared dependence. Now we can imagine a situation where I do not have any net magnetic dipole, so this first order term vanishes simply in an antiferromagnetic system, but I can still have ferroic ordering of any of these higher order multipole. And indeed such a situation actually takes place for all antiferromagnets that exhibit linear magnetoelectric effect. Linear magnetoelectric effect is basically described by the application of magnetic field that generates an electric polarization, and application of electric field that generates a net magnetization in the system. The effect was first discovered by Zyloshinsky in chromium 203, and it was consequently observed in the same system for the first time. Now you can see that for chromium 203 it has a collinear antiferromagnetic ordering, so this first order term indeed vanishes. But in this case we have a ferroic ordering of this magnetoelectric multipole, and in particular it has the diagonal elements of this magnetoelectric multipole matrix. Now there is an interesting correlation between the elements of this magnetoelectric multipole matrix and this linear magnetoelectric response. So if one of these elements exists, then the corresponding element in the response tensor also exists, which means that once we have a diagonal element in the magnetoelectric multipole tensor, we will have diagonal magnetoelectric response, which means if we apply an electric field, it would generate parallel magnetization. And this is not only true for chromium 203, but it is true for all antiferromagnets that break both inversion and time reversal symmetries. In the present talk, however, I will focus on those antiferromagnets that exhibit non-relativistic spin splitting, and these are actually some systems that are popularly known as altermagnets, and they have become popular because of their interesting property that they connect ferromagnets with conventional antiferromagnets, in the sense that they have splitting between up and down spin polarized bands very similar to ferromagnets, even in the absence of spin orbit coupling, while still maintaining zero net magnetization similar to conventional antiferromagnetic system. Now something interesting here is that this spin splitting pattern, as you see in the momentum space, that is very different from Rashba-like spin splitting, where the spin polarization direction actually is momentum dependent. Here it's always along Z. Of course, this is not the only type of pattern that you see in, possibly see in a system that exhibits non-relativistic spin splitting. There are different symmetry criteria, and depending on those different symmetries, you can actually see different patterns of spin splitting, even something that is antisymmetric with respect to K, unlike this one where the splitting energy is symmetric with respect to K. And in fact, these different types of symmetries, the properties that they emerge, this is something that we have recently actually summarized in this review article along with Orno. But in today's talk, I will focus on this particular type of spin splitting pattern. If you notice here, the spin splitting energy actually switches sign with the 90-degree rotation, and so it has like plus minus kind of behavior, which resembles to a D wave, and so this is called D wave spin splitting. And such D wave spin splitting actually occurs in inversion symmetric systems, antiferromagnets that break time reversal symmetry. Now for such a system, if we look at this interaction energy, the multipole expansion, then of course the first order term vanishes because we have an antiferromagnet, but at the same time the second order term also vanishes because I have inversion symmetry, and this term requires the presence of the broken inversion symmetry. And this makes magnetic octupole to be the first symmetry allowed ferroically ordered magnetic multipole in the system. But this is of course a symmetry based argument, and to verify this we explicitly looked into the case of Mn difluoride, which is already known as a candidate material for D wave spin splitting. Here, as you can see, there are two Mn ions, one at the corner and the one at the center of the unit cell. The MnF6 octahedral environment for these two Mn ions are rotated with respect to each other, and because of this rotation, time reversal plus translation is not a symmetry operation of the system, and so this actually breaks global time reversal symmetry. And as a consequence of this, when we calculate all the multipoles, we find that indeed there are two octupole components of this matrix that have ferroic ordering. And these particular octupole components, physically they represent an anisotropy in the magnetization density. The real space representation is x, y, and z, and as we can also visualize them from the band decomposed magnetization density, that the magnetization density around the Mn ions are highly anisotropic on this AB plane, describing these octupole components. Now, so we can see that we can visualize this antiferromagnetic MnF2 then as a ferroically ordered octupolar domain of MnF2. This has certain advantages. So for example, if we go back to the K-space representation of this anisotropic X, Y, and Z octupole component, that can be obtained simply by replacing R with K. This dictates where we have the spin splitting in the Brillouin zone. So anywhere in the Brillouin zone we go, if we have non-zero kx and ky simultaneously, we will see the spin splitting. And this is what we see here in our computed band structure as well. Going along 110 direction, there is a spin splitting. And with the reversal of the momentum direction, so this is actually here we are reversing only the ky that that generates an overall negative sign, and so the spin splitting actually switches here as well. So this magnetic octopolar picture is actually useful in understanding where we should look for the spin splitting in the band structure. Now another important point is that this anisotropic magnetization density actually follows from anisotropic charge density. So this means that if we can somehow control the anisotropic charge density by changing the position of the non-magnetic fluorine ion in the system, then we can possibly control this anisotropic magnetization density and so the magnetic octopoles. This possibly will control the magnitude of the the non-relativistic spin splitting, and with this idea we try to design a universal principle for controlling this non-relativistic spin splitting. And when we say we control the non-relativistic spin splitting, we mean controlling magnitude, sign as well as pattern of the non-relativistic spin splitting. If the time permits, then I will also discuss an analogous splitting in the magnon bands and how we can possibly control it, similar to the corresponding splitting in the electronic band structure. So these are the works that are primarily done by these three people, so Aniruddha, Muskan and Shubhodip, that I am going to present today. So first is the tuning of non-relativistic spin splitting. Here we are going to tune the magnitude of the non-relativistic spin splitting. So for MnF2, I already showed that there is an anisotropy in the charge density on the xy plane. So by some means, if we can control this anisotropy on the xy plane, we will be able to control the magnetic octopoles and hence the non-relativistic spin splitting. With this idea in mind, we looked at a particular strain. So this is a biaxial strain. The reason for looking at biaxial strain is that this is an in-plane strain, so it can control that xy anisotropy of the charge density and the magnetization density. So what you see is that with this biaxial strain, indeed my octopole components increase in magnitude. So with the compressive strain, the magnitude increases, and accordingly in the non-relativistic spin splitting, this is along gamma to n direction where we see that the non-relativistic spin splitting energy also increases in magnitude. So here we can control the non-relativistic spin splitting magnitude with the biaxial strain. The next case is when we want to control actually the sign of the non-relativistic spin splitting, and for this we looked into the case of barium copper fluoride. This is a geometric ferroelectric where there is a polar displacement of barium ions that are coupled to the displacement of the CuF6 octahedral environment. Now using an external electric field, if we can switch the direction of the polar displacement, that also switches the rotation of the CuF6 octahedral environment. And because of this switching of the CuF6 octahedral environment, there is a switching of the magnetic octopole, and accordingly even in the band structure we see a switching of the non-relativistic spin splitting. So the upspin, which was higher in energy before, becomes lower in energy, and the downspin becomes higher. So here we switch actually the sign of the non-relativistic spin splitting. Now comes a higher energy structure where actually this polar displacement as well as the octahedral rotation are suppressed. In this case, because of the suppression of this octahedral rotation, my magnetic octopoles vanish, and so this up and down spin polarized bands become doubly degenerate. So after showing the control of the non-relativistic spin splitting both in magnitude and sign. Now we are going to show that even we can control the pattern of the spin splitting. So for this we looked into the case of copper difluoride, which belongs to the same family of the transition metal difluoride series. So unlike MnF2 and other members of this family, copper difluoride actually crystallizes in a monoclinic structure. And it is also known that if we look at the band splitting, this is a schematic of that, this band splitting pattern is actually different in copper difluoride. It has an extra dependence on the bulk Kz direction, which is absent in the case of MnF2. So the question that we pose is what actually causes this difference in the pattern of the non-relativistic spin splitting, planar versus bulk. And of course, I should highlight here that copper difluoride has the exact same antiferromagnetic ordering as MnF2. So to understand this difference in the behavior of copper difluoride, we did the phonon analysis first, and what we realize is that this tetragonal structure of, this is an artificial structure for copper difluoride. So this artificial tetragonal structure of copper difluoride is actually connected to the monoclinic structure through an antipolar displacement of the fluorine ions. There are other distortions associated with it, but what predominates is this gamma 5 plus mode, which is the antipolar fluorine displacement. Now, if we can control this displacement mode, this particular phonon mode, what happens to my charge quadrupoles and the magnetic octopoles? Well, what we see here is that by controlling this distortion mode, we can actually introduce first a new anisotropic plane of the charge quadrupole. So this Q1 minus, for example, was 0 in the tetragonal structure, which now emerges in the system, and consequently this leads to an emergence of a new component of the octopole moment, which is this O3 minus. And once we have a new plane of anisotropy in the magnetization density, that consequently leads to a new direction of spin splitting. So for the tetragonal structure, I do not have any spin splitting along this gamma to KYKZ direction, but as I increase this gamma 5 plus mode distortion, my splitting in the band structure increases, and eventually it shows up. So with the introduction of this antipolar fluorine displacement, what I'm doing is that I'm introducing a new magnetic octopole components, which consequently introduces a new direction of spin splitting. And this additional direction of the spin splitting basically converts this planar D wave feature to a bulk D wave feature. Okay, so now that we have seen all the possible ways of controlling non-relativistic spin splitting in the electronic band structure, I would like to discuss the corresponding changes in the magnonic band. Sorry, this somehow got messed up, this figure here, but basically what happens here is that if we look at the corresponding spin Hamiltonian for this system, again I'm looking at Mn difluoride, there what happens is that we have a direction dependent exchange coupling, and this particularly takes place for the 7th neighbor exchange coupling. So going along 110 direction versus 1 minus 10 direction, the exchange coupling strengths are different, even though those are equidistant, and this happens because of the exchange path involved. So fluorine ions are, for example, present along the 110 direction versus 1 minus 10 direction, which makes this J7A stronger compared to J7B. And from our analytical calculation, we find that it is this difference in the exchange coupling that leads to a splitting in the magnon bands, and that particular splitting actually occurs again along the same gamma to M direction. So analogous to the electronic bands, I also have a splitting in the magnon bands of the system. Now, of course, the question is, can we control them? As we did in the case of electronic band splitting. So what we did here is that we first constructed the opposite structural domain of MnF2. As you can see, the structural rotations are now, octahedral rotation are now reversed between this corner and the central Mn ions. And now what we do is that we interpolate these two structures, and through interpolation we obtain this higher energy structure where these octahedral rotations are completely absent. Okay. Now we try to understand how this high energy unrotated MnF6 octahedral environment structure is connected to the ground state structure. These are connected by two particular phonon modes, A2U phonon mode, which basically describes the displacement of the fluorine ions along C direction, and then there is also A1G phonon mode, which describes an in-plane displacement of the fluorine ions. Now, the idea is that by controlling this two phonon mode, these coupled phonon modes, can we control the spin splitting? And why do we actually expect that even can happen? Well, we know that what causes the splitting in the magnon bands is this direction dependent exchange coupling related to the position of the fluorine ions. So by these two phonon modes, if we can control the position of the fluorine ions, we will be able to control the magnon splitting as well. So with this idea, basically we moved forward and we did the calculation, and we indeed find that this difference in the seventh neighbor exchange coupling, which causes the magnon splitting, can be controlled by these two phonon modes. And in fact, this explicitly vanishes at 100% distortion. By 100% distortion, I mean this high energy reference structure. And consequently, in the magnon band, the splitting completely disappears. So there is a possible way to actually control the magnon splitting as well. Now, quickly look at what happens to the electronic bands. Before that, let's look at the magnetization density. We already discussed the 0% case where the magnetization density was highly anisotropic. Now that we introduce this distortion, for this 100% distortion, the magnetization density is now symmetric along 110 and 1 10 direction, and in fact for this structure the octopoles vanishes. So we have basically a transition from an unconventional antiferromagnet with ferromagneto-octopolar order to an antiferromagnet where the spin splitting in the electronic bands also disappears, so with no ferromagneto-octopolar ordering. Okay, so with this I would like to summarize that this octopolar picture is actually useful in understanding many physical effects, in particular the role of the structural distortion and how we can control them using external perturbation in order to control the non-relativistic spin splitting without even changing the Néel order. This of course opens up a lot of new questions. For example, what are the effects of this magnon splitting in different transport properties? For example, thermal transport properties. There any possible interplay between topology and the non-relativistic spin splitting that we see in real electronic band structure or even magnonic bands. Of course, these are theoretical prediction, and more experiments need to show up to verify all these proposals that we have. So with this, I would like to acknowledge all my collaborators who were involved in the work, funding from IIT Bombay, DST Inspire, NRF, and also computational facility provided by National Supercomputing Mission. Thank you all for listening.
Thank you. Yeah.
So quick question. So in your magnon splitting, why seventh neighbor?
Yeah, because this difference, actually the magnon splitting is very small in magnitude, and that happens only for the reason that there is an exchange coupling which has this direction dependence, and this direction dependence comes for the seventh neighbor because of the exchange path. In one of the path you have fluorine ions in between, whereas for the other path it does not. So even though those are equidistant, the exchange couplings are not.
Fluorine.
Yeah, yeah.
Thank you, nice talk. Ma'am, I will ask a technical question. So, I read this paper, I will start the calculation. So the I will shift the origins. So, point by point from the center in the method part.
Oh, you mean, I guess you are referring to this structure, are you?
Yeah.
This one?
No, I in this paper, this you shift the origin from in the calculation part, point by.
So, so you can visualize this structure, okay, as if you are shifting the origin by half, so that your original central atom becomes the corner atom now, okay. The other way of generating this structure is to basically change the position of the fluorine ion from Y-cup side symmetry 4F to 4G, which is also a symmetry allowed position.
Okay, and another question is the distortion is the mainly origin to produce the octahedral magnetic octapoles and charged quadrupoles, or
yes. Yes, so we actually have a more detailed study about this. I'm just looking for that reference. Yes, this paper where we actually did a thorough study of different phonon modes and how they possibly can affect your anisotropy in the charge and magnetization density. Physically, you can think it like this. So if you have some distortion, that obviously affects the electron distribution, right? So your octahedral distortion particularly guides how your charge and magnetization density distribution will be around the magnetic ions, and by these different multiples we are basically quantifying those charge and magnetization density anisotropy. So yes, so everything you can actually understand from the distortion itself, and in fact figuring out the correct distortion that leads to that anisotropy is the key thing here, because once you identify the correct distortion, you can think about an external perturbation that controls it.
Like
electric field or strain, for example, as we discussed. Yeah.
First of all, thank you so much. As usual, I mean, maybe I asked already this question in several of your presentations, but I forgot again. So this Yantala-like distortion against your 100% distorted GFO type distortion, I mean, they are completely different potential energy surface. I mean, they are
different potential
energy surface stability, right? Because they are completely different geometry. And in that particular case, I mean, how do you expect the correlation of the phonon modes between that to this lead to your expected?
Well, so I don't know. So for example, in this case, okay,
this case,
so this is
the other one that you saw, this
right.
volcanic one.
Okay, so let me first discuss this one, and then we can go to the next one. So this is actually the A1G phonon mode. Okay, so I did not discuss it in detail during the presentation. So basically, with biaxial strain, what you are controlling is the A1G phonon mode. A1G phonon mode is already present in your structure. It's just that with the external strain, you are changing the amplitude of it, and accordingly you are changing the octopoles and the spin splitting magnitude. Okay. Now coming to the next part, where we have jointly controlled these two phonon modes. Of course, in the calculation it's easy. Now comes the practical part. So one hope is that, so this A2U is infrared active. Okay. So with optical excitations or electric field application, you can control A2U phonon mode. Now this so we actually studied it in detail, and this A2U phonon mode is also coupled to the A1G phonon mode. So once you, although A1G is Raman active, when you excite this A2U phonon mode, because of the coupling, A1G phonon mode also.
All are gamma point, right?
All are gamma point, yes.
This is what I believe, that a good one dispersion may lead to you different scenario, that which atoms contributing in this structure.
Well, we don't want to go beyond gamma point phonon modes. The reason is that, reason is that we don't want to increase the unit cell size. If we increase the unit cell size, no, but then the non-relativistic spin splitting will be different. So one of the main criteria for the non-relativistic spin splitting is that you have to break the time reversal symmetry, and this breaking of time reversal symmetry happens for the case when your magnetic unit cell is the same as your structural unit cell. So we don't want to go for the supercell cases. So that's why the particular focus was on the gamma polymer.
Last question.
Nice talk, ma'am. Ma'am, there is one question. Ma'am, although the material is globally antiferromagnetic and locally the material is ferromagnetic, but what is the reason for the
It's
spin
not
splitting?
what do you mean by locally ferromagnetic?
Ma'am, locally means for certain sites the material spins are like
Okay.
arranged on some
Okay.
particular direction. So the just want to ask them why the spin splitting along a certain billion joule path means like
Yeah.
from
So
your two different symmetries, like
So-
we can get the spin splitting to the whole billion.
yeah, so there are two ways of actually understanding this. One is that you can do either a thorough spin group theory analysis. From there you can figure out which direction would be the spin splitting, but here the method that I discuss is we try to figure out what is the relevant multipole and what is the corresponding case space representation. So for example, in our system we have anisotropy in the magnetization density, right? Overall the system is antiferromagnetic, so there cannot be any net splitting between up and down spin polarized bands once you integrate it over the Brillouin zone. What we can at most have is certain direction where the spin splitting occurs, and then that has to reverse back so that once we sum them up we get a zero value. Okay. Now your question is which direction this splitting occurs. Well, that is dictated by the anisotropy of the magnetization density. In particular, in this MnF2 case, the anisotropy is on the xy plane. So in the reciprocal space also you see the spin splitting along any direction in the Brillouin zone that has simultaneous non-zero kx and non-zero ky. Okay, so basically you have to identify the anisotropy plane of your magnetization density. Yeah.
All right. So let's thank the speaker again. So the next